Mr. Tarou, in this math lesson we're going to do 3 examples that involve the dot product, scalar product, or inner product, whatever your textbook is calling it. This geometric definition after we look at some properties of scalar product. We're going to save the discussion for the more algebraic form of the dot product or scalar product, inner product for our next lesson. In the description of this video you'll find timestamps to the 3 examples. They'll go from basically easy to fairly difficult quite quickly. You'll also find a link to my playlist that involves or has all of the lessons I've done so far on vectors. Okay, I've also shown the relationship, kind of did a partial derivation and showed you where this formula for dot product or scalar product comes from, and also how it relates to the algebraic definition that we use when we have these vectors written in component form. That's in the playlist for all my vector lessons. So let's get the definition of the way. Given 2 non-zero vectors, vector u and vector v, the dot product or scalar product, inner product, between vector u and vector v is equal to the magnitude of u times the magnitude of v times the cosine of theta, where theta is the angle between those 2 vectors. And multiplication is commutative, so you can also write this with vector v first and vector magnitude of vector v and magnitude of vector u then afterwards. Now definition, okay. Vectors are defined by their magnitude and direction, not their initial point. But if you want to talk about an angle between 2 vectors, we kind of need to assume, therefore, these vectors are sharing an initial point. So here we have our vector theta between these, and we have that same initial point, so we can measure the angle between those 2 vectors. And your textbook probably has these 2 vectors written or drawn out in a diagram with the same initial point, but there's a smaller ray that's called a projection. And this is called a projection of vector v in the direction of u. It's basically, again, that part of the component, that component vector of v that goes along that direction of vector u. So when you take a dot product or a scalar product between 2 vectors, you always get a numerical value. And that numerical value is just basically multiplying the lengths, the magnitudes of 2 vectors that are going in the same direction. Some of our products of dot products, the scalar product of 2 vectors is always a number. Again, it's just you're basically multiplying 2 magnitudes. The definition of a scalar product does not depend on the dimensions of the space. Now, in the books that I'm working out of, and I am only basically, I'm only a high school teacher, my experience is only with dealing with 2 and 3 space vectors. They do go beyond that, which I don't necessarily comprehend. But basically this is just saying that your definition for dot product, scalar product, inner product will work for 2 dimensions and 3 dimensions. You don't get a new definition when you go into 3 space. The dot product of vector v and vector, that's u. The dot product of vector u and v is equal to 0 if and only if either vector u is the null, trivial, or 0 vector, where all components of vector u are equal to 0, or vector v is a 0 vector, or, which is a bit more interesting and what you'll be dealing with more often, vector u and vector v are orthogonal, which is kind of just a fancy word for perpendicular. There's a very, very slight difference, but the idea of orthogonal vectors, that language is, that vocabulary is used a lot with vectors. And it's pretty easy to understand where this is coming from, especially with this idea that the 2 vectors are orthogonal, perpendicular, meet at a right angle. If you know your unit circle, the cosine is basically your x-coordinates around a unit circle. Circle, of course, we know has a radius of 1, and cosine of 0 is 1. Cosine of pi over 2, or cosine of 90 degrees, is equal to 0. And cosine of 180 or pi is -1, and so on and so on. Well, look here. I mean, cosine of theta is part of our definition for the scalar product between 2 vectors. Yeah, and the cosine of 90 degrees is equal to 0. So there you go. If your dot product is equal to 0 between 2 vectors, you're showing, or that's proving, that those 2 vectors are orthogonal. The scalar product or inner product of vector u and vector v, I'm going to try and keep the cycle through these 3 names, is equal to plus or minus the magnitude of vector u times the magnitude of vector v if vector u and vector v are parallel. Now parallel is a little bit more open than two vectors going in the same direction. You can have vectors which are directed line segments that are parallel when they go in the same direction. They can also be going in opposite directions. What's the cosine of 0? If the angle between your two vectors is 0 degrees, then they're both going in the same direction. The cosine of 0 is equal to 1, positive 1. And if the angle between your two vectors is 180 degrees or pi radians, so they're opposite vectors but they're parallel, well, the cosine of 180 degrees is equal to negative 1. So there's your plus or minus, and the reason why there's no cosine after the magnitude of these two vectors multiplied together is because it's either 1 or negative 1. So the dot product between vector u and vector u is the magnitude of vector u squared. You can do a little diagram here, and it's a little bit weird to think of this in terms of the geometric definition. You can draw a little vector here and say this is vector u, and you have a component of which has a length of u sub 1 and a vertical component which is a length of u sub 2 if you're defining the terminal point as u sub 1, u sub 2, and just think that u sub 1 squared plus u sub 2 squared is equal to, well, it's equal to this length squared, or you can think of the magnitude of vector u is equal to the square root of u sub 1 squared plus u sub 2 squared, and then square both sides and get the magnitude of vector u squared is equal to u sub 1 squared plus u sub 2 squared. Now, this is a little bit easier to understand. I'm pausing because I wanted to do all this in terms of the geometric definition of dot product, but it's actually a little bit easier if you think about this in terms of the algebraic definition. And so I'm going off on a random tangent I didn't intend to, but the dot product of u and v is u sub 1 v sub 1 plus u sub 2 v sub 2. And if you're just simply dot prodding a vector with itself, well, then it's u sub 1 times u sub 1 plus u sub 2, not v, u sub 2 again. Well, u sub 1 times u sub 1 is u sub 1 squared, and u sub 2 times u sub 2 is u sub 2 squared, which is the length of the third side of your, it's just Pythagorean theorem, the length of your hypotenuse squared. And length in vector format is used, described with this magnitude notation. So some of our other properties of scalar product, inner product, dot product of vectors is the dot product of two vectors is greater than 0 when theta is acute. The dot product of two vectors, scalar product, inner product, is less than 0 when theta is obtuse. It's really easy to understand when you're looking at this definition of scalar product, inner product, dot product. If your angle is acute and you're in quadrant 1, cosine is positive in quadrant 1. If you're in quadrant 2, greater than 90 degrees, cosine is negative. Then we've got some other properties here. Basically, your dot product is commutative. Commutative. And you can do the distributive property with the dot product. The dot product of vector u times vector v plus vector w is, you can just take that dot product and have the dot product of vector u with vector v plus, and distributing again the dot product of u with the dot product of w. And you can work with sort of like a regrouping or associative property with a scalar multiple of lambda. This is just saying, like, take a vector, make it, if this is u, 2 times vector u, just changing the scalar multiple, which is changing the amplitude. You can apply that scalar multiple with 2, 1 vector and then do the dot product, or you can do the dot product between those two vectors first and then apply your scalar multiple to that numerical value that you always get from your dot product. Okay, our first example is coming up right now. It's fairly straightforward, and we'll bump into some more complicated problems pretty quickly, for example, to an example 3. Alrighty, example 1. Consider rectangle ABCD. Find the inner product between vector DO and DC. Okay. Well, we've got this orange rectangle, and what we are really going to be concerned with, since we're just looking at vector DO and DC, I'm going to just pull this out just to give a little bit of extra clarity, and we're looking at these two vectors. Okay, well, the formula for the scalar product is, of course, magnitude of each vector multiplied together times the cosine of that interior or included angle. And we already know that the magnitude of vector DC is equal to 7 square root of 3. It's just given to us right there on the rectangle. That's opposite sides are equal. Vector DO. Okay, so how long is this? Well, can't find it like right off the bat necessarily, except if we just look at the information given, and that's part of the reason why I pulled this portion of the rectangle out. Just look at those two sides and think about some special triangles from geometry. You know, there was 2 that we always had to work with when setting up the unit circle, the 45-45 triangle, and the 60-30 right triangle. So hopefully you recognize that. If you've got a side that's some arbitrary length, the other side, the other leg that makes that right triangle is the same arbitrary length, only multiplied by the square root of 3. Well, 1, 2, thinking of the answer, 1 square root of 3 means the hypotenuse is twice as long, which means that this entire length is 2 times 7, or 14. And we're also going to have to remember not only that little bit of 60-30 ratio from geometry, but we also know that if you have diagonals for a rectangle, that they're going to bisect each other. So since DB is a diagonal and AC is a diagonal, where they intersect bisects, so while this entire length is equal to 14, the magnitude of DO is equal to 7. So we come over here, keep looking at our formula and letting it tell us what we need to figure out. The magnitude of vector DO is equal to 7. Now, we just filled out that last side of the right triangle. Of course, you could have just done Pythagorean theorem as well. But if you recognize that 1, 2 square root of 3 pattern, then you'll know that this is a 60-30 triangle, and the cosine of 30 degrees on the unit circle is square root of 3 over 2. It's really a bad idea to write equals next to every line of work. It's probably fine if you're just taking a class and your teacher is cool with, or just not thinking about, because I never did, the implications of that. But if you're going to ultimately take an AP test or IB test, they're going to see that line of work and they're going to go, oh, okay, you got your notation that says it's equal to this expression, and it's equal to this, and equal to this, and equal to this. If you make a small error or just do some scratch work and just by habit put an equal sign there, if that particular line of work is not equal to your original expression, they're going to call that a linking error and stop grading, and you're going to lose a lot of points. Okay, so what's going on here? We have 40 times 3, which is 120. We have 9 times 3, which is, of course, what? 27. And so we're looking at 147 over 2. And I've already done the solutions for this, and I feel like I'm making a mistake somewhere. My mistake is in my pre-made solutions. I said the square root of 3 times the square root of 3 is equal to 9, which of course it is not. So we have that over 2, and we have the scalar product. Teachers make mistakes too. I make more than I would like to admit. We have 147 over 2, which is going to, I guess if we want to take the time to make this a decimal, it's going to be what? 73.5. And it's not degrees. You're not finding the measure of some angle. It's basically, remember, you're multiplying two magnitudes for vectors that are going in the same direction. Some vector and a projection of another vector onto that one vector that's going in the same direction. So this is just a scalar multiple, and it's 73.5 units. That's the end of our first example. Second one coming up right now. Example 2, a triangle ABC has an area of 6. Given that AB is equal to 3 and AC is equal to 6, find all possible values for the inner product of vector AB and AC. Scalar product, dot product. Why do I have so many names? Okay, well, it's a geometry problem, which means at some point we're going to draw a diagram. But like all questions in math, especially ones that you find a little bit complicated, you want to read the problem, pull out important information, maybe make a diagram like we're going to do, and also don't forget to let the question tell you what you need. You're looking for all possible values of some dot product. So we need to work out or fill out this formula of vector AB, well, that's an ugly A, and AC, which is the magnitude of vector AB times the magnitude of vector AC times the cosine of theta. Okay. Man, that must be giving us a really easy question. I mean, I want the magnitude of vector AB. Now this is identified as a length of a line segment, but vectors are directed line segments, so that's 3. Vector AC is going to have a length of 6. All we got to work out is what's cosine of theta. This isn't too bad, right? And it kind of isn't, but you do need to take the time to look at this graphically. We have some triangle ABC, and AB is 3. Wow, this is going to look like it's the same length. Let's just at least make it seem reasonable in the sketch. AC is 6. Not that diagrams have to be drawn to scale, as your old geometry book used to warn constantly. Now, if we're looking for the scalar product between and its possible values between vector AB and AC, we have everything except for the cosine of theta. And that means that theta, if we're going to find the cosine of theta for the dot product, it has to be between the two vectors. So this is our theta. We're not looking for angle B or angle C. We're looking for angle A. We've used everything so far except for the area of this triangle, and whatever. We have to use that angle, that area of 6. Now we have 3 formulas for area. One is Heron's formula, where we find the perimeter and divide it by 2, and then this big long square root of blah, 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 blah. You have simple 1/2 base times height, and then you've got another formula that says that the area of a triangle is equal to the length 1/2. The length of two sides in this case is going to be the length of AB times the length of AC times the sine of theta, the sine of the angle between those two sides. Now, why is this the formula that I'm going to want to use? Well, not only does it fit the information in the problem, but 1/2 base times height is not going to directly take us to, or as directly take us to knowing some kind of ratio for the cosine of theta, nor does Heron's formula use a trig function in it. And this is a non-calculator question. So we're not really going to have the ability to find out what theta is equal to, but we're going to have to use our trigonometric skills to work through this problem. So we have 1/2, our area is equal to 6, AB is a length of 3, AC is a length of 6, and we have the sine of theta. So the only unknown is the sine of theta. Now if I can find out what the sine of theta is, I can remember like what we did so many times in trigonometry where you were given some kind of trig ratio, and if we just assume it's in quadrant 1, then we can set up a little right triangle and find all the other 5 trig functions. If we open the door up to other quadrants, we have to have one more piece of information, like maybe the sine of another trig function. But we have 6 is equal to half of 6 is 3, and 3 times 3 is 9. Divide both sides by 9 and reduce the fraction, and we have 2/3 is equal to the sine of theta. And without a calculator, we need to go from the sine of theta, which is a ratio of 2/3, to come up with a ratio for the cosine of theta. That shouldn't be too bad. Do this in green. We have, think about a little right triangle in quadrant 1. Let this be theta. The sine of theta, it has to be a right triangle because we're not doing like law of sine or law of cosine. I know this is not a right triangle, but your 6 trig functions are based off the ratios of right triangle. Opposite over hypotenuse, or y over r. A little bit of Pythagorean theorem. The square root of 9 minus 4 is going to be 5. So it looks like from this diagram that the cosine of theta is equal to square root of 5 over 3. So we have, let's do this in green because it works with this diagram. Cosine of theta now is going to be, from this diagram, square root of 5 over 3. 3's cancel out, and we have 6 square root of 5. Now, if that's all you put down in your answer, then you have shown a lot of understanding. You wrote down the formula that ties to the question. You have realized this is a geometry problem. You've given yourself a diagram. You filled out some information. You pulled out of your hat the appropriate area of a triangle formula that is useful in this question. You showed how to convert from a sine trig function, take that ratio and create another ratio for cosine. You've shown a lot, and you're going to get most of these points, but you're not going to get all of them. There's a reason why this said to find the possible values. It's a hint there. There's more than one answer. This is a positive ratio for sine. Remember when I said, as I was kind of trying to recall some knowledge for you to help you through this problem and understand what I'm about to do? This is just assuming that we're in quadrant 1. If we open the door to other quadrants, we have to know some additional information like the sine, not S-I-N-E, but S-I-G-N, the positive negative nature of another trig function. And we don't have that. All we know is the sine is a positive ratio. Well, sine is positive both in quadrant 1 and in quadrant 2. And if I draw this same ratio of 2/3 y over r, there's no such thing as a negative length, but we can have positive negative to indicate direction. Instead of moving to the right square root of 5, we can move to the left square root of 5. And here in quadrant 2, our cosine is going to be negative, so our other answer, our other possible value, is coming from 3 times 6 times the cosine of theta in quadrant 2 is negative square root of 5 over 3. And our final answer is negative 6 square root of 5. And these are two possible values for what we could get from doing the scalar product, inner product, dot product of vector A, B, dot vector A, C. Third example coming up right now. It's the last example. Example. There's no question. What are we doing? We are going to look at this cuboid, A, B, C, D, E, F, G, and we're going to find the scalar product of vector OB and OC. Okay. Cuboid, which just means this is, you might call this a rectangular solid. All the corners are all these segments are meeting in 90 degrees or are perpendicular. So how are we going to do this? Well, we're going to find the vector or the scalar product, inner product, dot product of vector OB and OC. We're going to be looking at the magnitude of OB times magnitude of OC times the cosine of theta. So what we're really concerned about is working with this triangle here, and theta is going to be between vectors OB and OC. And just for clarity's sake, I think I'm just going to take this out. I know that this length is 3, but that's really not going to be very useful for directly substituting into this question. So yeah, we have a lot to find here. Okay, so let's start somewhere. We need to recognize that this is a cuboid, so there's a plane here, plane EHCB, or maybe just think of it as a rectangle. And that's a rectangle. I'm sure there's some distortion with my drawing, but that's supposed to be a rectangle because this is a cuboid. Oh my goodness, that's nowhere near straight. But at any rate, this is diagonal H, B, and E, C. Those diagonals, because this is a rectangle, are equal. And like the last problem, those diagonals, when you have diagonals going through a rectangle, they're going to bisect each other. That's true with any parallelogram, but they're not just bisecting each other. Each of these diagonals are also equal. So these two legs, while I still don't know what the lengths are, they're isosceles. So we're looking at finding the lengths of an isosceles triangle. Now we do have some information here of 3, 7, and 4, none of which are directly measurements of these segments, the magnitudes of these vectors that we need to find. But you know what? We do have vector notation up here, and while I can't directly go to finding the magnitude of vector OC, or basically the length of this line segment, I can look at the magnitude of vector CE. Now the magnitude of vector CE, or basically just if I take out the direction portion of it, just want to find the length of this line segment. You can find that just full-blown, like just using pure algebra in geometry, actually, is what I mean to say, and kind of build our way up there. Even though we're studying vectors, I really try to get my kids to see the geometry in these as well and see the relationship between this current course and the previous ones we've been into. So this is going to be the long way around here, but if you bear with me a little bit, there's going to be lines all over this diagram, but there is a right triangle in the base of this cuboid. This is going to be a big ol' right angle here. And if we can find the length of this hypotenuse, the length of AC, that's going to help us find the length of EC, just moving through this 3 space, because we're moving from a right triangle that's in the flat horizontal plane maybe we could just assume it's horizontal plane of this cuboid. That's going to allow us to move up to a perpendicular triangle that's in the plane of AEC, but we'll just have another right triangle here. And the hypotenuse of this green right triangle is going to be the leg of the red right triangle. And you can go through Pythagorean theorem again and find the length of EC. Now this is, I'm not using or thinking vectors here, and this is a longer way of going through it, but then I'm going to show you how this works in vector notation. And it's going to be quicker, but you'll see that the answer is valid, other than maybe your teacher wrote it, so you're assuming it's right. It works because he said so. We have this triangle here in green. A, B, C, a leg of 7, leg of 3, and Pythagorean theorem is going to say that AC is the square root of these two legs squared and added together, so we have 7 squared plus 3 squared. It's going to be the square root of 49 plus 9. We have AC is the square root of 58. And just to make sure I don't carry some silly mistake and nope, move through the rest of the problem unknowingly, because you and the camera can't yell at me and say I've written something wrong. We're then going to move on to this red triangle now. AEC. AE is 4. AC, this leg, is this green triangle's hypotenuse, which is going to be square root of 58. And then EC is equal to the not using or using vector notation right now. Let's not use the word magnitude, but its length is equal to 4 squared plus the square root of 58 squared. That is going to be the square root of 16 plus 58. The square root cancels out the square, and we get the square root of 58. 68 plus 6 is 74. So if EC, well, yeah, okay, yeah, so line segment EC is the square root of 74. Now, you could also look at the problem this way. I'm going to do the direction this way, but just for notation. Vector EC is the resultant of going from E to C. It's EA, vector EA, plus, now from there we go from A to B, doing this triangular method of addition of vectors. Then from B we go to C, and we have plus vector BC. Now, if all these vectors were in component forms, we could add the components along the, because this is in 3 space, if we had these 3 vectors in component form, we would add the 3 components along the direction of the x-axis, the 3 components that go in the direction of the y-axis, and the 3 components that go along in the direction of the z-axis. We would get some new vector EC that's in those 3 components, x, y, and z, and then to find its magnitude, the magnitude of EC would be the square root of each of those components. Maybe just say it's u sub 1 squared plus u sub 2 squared plus u sub 3 squared. In each direction we have a certain magnitude which would be in that component form, and we would just square all those and add them together. Well, we have some component length, some magnitude in the direction of the x-axis, if you will, the y-axis and the z-axis, if you're thinking about what 3 space looks like, x-axis, y-axis, and z-axis. And really, you know, to get from E to C, our component on the x-axis is really, because we're going from the front of this cuboid to the back, would be -3. The y component would be a +7, and the vertical component would be down 4. So actually, I could write that, couldn't I? I'm going to do it in a horizontal component format because I've run out of room, but vector EC is front to back. So along the x-axis, we're going back 3. We're going from left to right, and that left to right movement on the y-axis is going to make those numbers positive. So we're going from left to right. So that's going to be y component of 7. And we move down the z-axis. So our z component is going to be -4. So the magnitude of vector EC is equal to the square root of -3 squared plus 7 squared plus -4 squared. That's going to be the square root of 9 plus 49 plus 16. That is going to be the square root of 49, 59. 59 and 6 is 65. And 65 and 9 is 74. That was a lot less work than seeing it geometrically and moving, with right triangles through these planes, the horizontal base plane and then the sort of vertical plane here between coordinates of A, E, and C. But you can see that you can take these problems and approach them and think about them in different fashions and get those same values. Now, going back to the fact that we're trying to find the dot product of OB and OC, well, now we know that the base there is 3. And since this entire length of EC is the square root of 74, and these diagonals are going to bisect each other, each of these legs is equal to the square root of 74 over 2. And now we have a lot of stuff in the way, but our scalar product is going to be equal to the square root of 74 over 2 times the square root of 74 over 2 times the cosine. Now we just have to find out what cosine of theta is. And again, just being super cautious, I do not want to make a mistake and carry this through the whole whoop-de-doo. We need to find out what cosine of angle O is. So our last piece of the puzzle is, what is that cosine of theta? Well, we have a non-right triangle with all 3 sides known, so we're looking at 3 squared is equal to the other 2 sides squared and added together. Hopefully I found a good problem for you that you're finding interesting. I made one inspired by a book problem, but made up. So one side squared and added together is equal to the other 2 sides squared and added together minus 2 times the length of those other 2 sides times the cosine of theta. So we have 9. These are going to come over with subtraction, so 9 minus 74 over 4. Just squaring the numerator and denominator, moving it over. Same thing here. We're going to type all this in our calculator at one time. We'll cancel out. -1/2. Square root of 74 times square root of 74 is equal to 74. So now this -74 over 2 is going to get multiplied. You're going to multiply both sides by the reciprocal. And that is going to come out to be, right off the top of my head, I'm not really rounding this off. I'm going to 14. So I got a little quiet there because in my when I made these video notes, I did the inverse cosine of this, and I got the measure of theta, and I rounded off to, I think, 6 decimal places after, to 6 decimal places, and then did the cosine of that angle, and I got 13.9998. So it's close, but actually keep it in this format. This, in exact form, was 28 over 37. And even though I changed these numbers, and while this is inspired by a problem in the textbook I'm teaching from, it's not the same. I made up my own, changed my own numbers, but without the round-off error that I did originally in my creation of these notes, you keep everything in exact format, you get exactly 14. So it's just a little bit of cautionary note as well, that as you're doing these problems, don't round off until you get to the end. And if you're allowed to round off to 3 decimal places, you only round to 3 decimal places when you're done with the final problem. If I came up to maybe 13.998 or 13.98, if I rounded off really too much, I might lose some points at the end when we're looking for an exact answer of 14, though that was honestly unintentional. If you don't get that exact value and you're off too much because you rounded off too early or just within your work, you'll lose some points even though you understand all the math that you're doing. I'm Mr. True. Bam! Go to your homework.